Now recording on this computer.
Fantastic.
Cool, very good. So I think we should start things off now. So welcome everybody to the latest installment of the Shocklab seminar series. We're really happy to have Callum and Sasha here today to talk about their work, along with Claude and Rowan and others from InstaDeep working on this MARL software ecosystem. They've talked to us about some of it in the past, but yeah, super excited to hear more details now. So guys, over to you.
Awesome. Thanks so much. Yeah, we're going to be, well, I guess, firstly, I'm Sasha. I'm a research engineer at InstaDeep, but I think most of you guys know me. Yeah, we're going to be talking you through the kind of growing and what we're building as a MARL ecosystem in JAX. Something that kind of lends itself to fast research iteration, but also super scalable and flexible, and also really well maintained, or we like to believe it is. Yeah, so firstly, the team, it's a really big team right now. There's a lot of us, but that's not all, because we're kind of standing on the shoulders of giants. There's a lot of past contributors to Mava. I think you guys will recognize some of yourselves here. But like also past contributors to environments, all of kind of Jumanji's contributors, there's a huge, effort around this entire ecosystem. Yeah, so why build an ecosystem? Why are we doing this? At its core, we really want to solve kind of hard multi-agent problems. We want to be like, we want to be able to scale to problems that could, take days, need like massive networks, thousands of agents, stuff like this. And to do this, we really need to push the MARL research frontier with new environments, new novel algorithmic contributions, that kind of thing. And to do that, you need software that is reliable, flexible, and scalable. Reliable in that we know that it works, it's tested well, all that kind of stuff. Flexible in that it's easily hackable. You can take let's say PPO as a starting point, and easily, you don't have to learn how the library works. It's just all there for you. You can hack it, you can change it super fast, sort of clean RL inspired. But at the same time, we want it to be, really scalable, in that you can run this on multiple devices, you can generate huge amounts of experience, and really fast, that sort of thing. And supporting this, hackability and scalability is stable and maintained tooling. So this is all the stuff around the algorithms, the environments, the logging, the replay buffers, all this kind of stuff. Yeah, and then finally, you really got to have robust evaluation methods in order to kind of standardize as a community, as a MARL community, to standardize our outputs, and so that we have a standard way of comparing our own results. Yeah, so that takes us to this picture, our MARL ecosystem. So on the left, you can see that we've got kind of our maintained, like super stable software tools. So that's our environments, our replay buffers, and our evaluation and logging stuff. And then in the middle, you've got our two kind of algorithmic hubs, if you will, being Mava and OG MARL, so online and offline multi-agent RL. And then on the right, you've got kind of the output of all of this, being papers, data sets, and evaluation kind of artifacts. Yeah, so just I think quite a few of you here have used JAX and know what it is, but just in order to kind of be able to understand some of what's coming, a primer on JAX. So JAX is just NumPy that can compile to XLA. XLA is like a language or an intermediate representation that works super well on TPUs and GPUs. And so one thing that JAX is that it's functional, and so it's got a lot of transforms that will transform a function essentially. So the three that you need to know for this talk is JIT, VMAP, and PMAP. So JIT, which stands for just-in-time compile, takes some function and compiles it. And so, you go from Python interpreter speed to a really fast, compiled function. And then you've got VMAP, which just vectorizes a function. So you'll write something that takes in a single input and it'll vectorize it, hopefully run it across CPU cores, that kind of thing, or CPU threads. And so you'll get some speed up from that. And then you've got PMAP, which can distribute across multiple devices, so multiple GPUs or multiple TPU cores, that sort of thing. Yeah. Cool. So this is the whole ecosystem, and I'm going to start off by talking about Jumanji. So what is Jumanji? It's kind of native JAX RL environments. It's specifically industry focused and specifically, or not specifically, but largely focused on combinatorial problems. And so you might ask yourself, like, we've got Gem, why do we want Jumanji? And the reason for this is that we want to be able to end-to-end compile and put on an accelerator our algorithms. So if you just had, a regular PyTorch or NumPy implementation of your environment, you wouldn't be able to put it on an accelerator, at least not easily. But with a JAX implementation, you can put your algorithm, your network forward pass, your environment step all on an accelerator. And so it's super, super fast. So yeah, just to take you through a super short code snippet of like what Jumanji looks like and how it feels like to use. Yeah, it's pip installable, so easy in that sense. It's got a familiar DMN style API. So you've got like your make and then your steps return a time step object. It's got, very reproducible rollouts. So this is a really nice feature of JAX, which is basically that every random call needs to be seeded. And so if you pass in the same actions with the same initial random key, you'll get exactly the same output, which is really, really useful. It's got rendering, so you can, make nice GIFs like this one. And then you can also JIT or PMAP your environment. So again, you can put it on an accelerator and you can put your environment or multiple copies of your environment on multiple devices and just generate ridiculous amounts of data. So yeah, just to go over what environments we have. So in Jumanji currently there are, I guess currently it's both single agent and multi-agent. However, I'm just going to talk about the multi-agent environments because it's a multi-agent ecosystem talk. But yeah, currently we have robot warehouse and level-based foraging, which are existing environments from the literature made by the team at Edinburgh. And basically we took those environments and we rewrote them in JAX and put them in Jumanji. But yeah, now we've, took this opportunity that we have Jumanji to also make some new and hopefully useful multi-agent environments. So we've got cleaner as the first one, where you've got multiple agents that need to clean this grid. Connector, where you've got multiple, snakes, I guess, that need to connect to their targets but can't overlap each other. And then you've got multi-capacitor vehicle routing, which is like a multi-agent traveling salesman problem. Yeah. So that's Jumanji, and how it fits into the ecosystem is that it's basically the base API for Marva environments. That being said, we don't only support Jumanji. We want this to be an open ecosystem, and we want to use other environments. So specifically right now we support JAX-MARL, and they've got a whole lot of environments, and then we also support GigaStep, which is kind of a new environment that was released at NeurIPS last year, I think. Yeah, and so it forms the base API, so you just kind of have to write a wrapper and it'll work. But yeah, to go on to Marva. Marva is our collection of online RL algorithms, and why we think it's super nice and useful is because it's very inspired by pure JAX-RL or clean RL, in that it's super hackable. It's not like what Jumanji is a library that we want you to pip install and use. We don't want you to pip install Marva. We want you to clone Marva and use it, like edit the algorithm, copy and paste code, and hack it all together. Yeah. So specifically, Marva is distributed and scalable online RL or online MARL algorithms, and we use the Anakin framework to like distribute and scale our code. And this is something that you can do when your environments are written in JAX, and you can put them on an accelerator. And so this picture is basically a representation of that, and it's quite a complicated picture. So to dive a little deeper, you've got like your environment and your acting step initially, and so we will VMAP that acting step. So you'll have multiple copies of your environment akin to like a gym multi-process wrapper. But usually this is running on a GPU, so you kind of get like massive amounts of parallelism much easier. But we don't stop there. We then VMAP the acting and learning loop as well. So you'll have multiple copies of your environments, right? And then we'll VMAP over those multiple copies plus the learning. So you'll do like, maybe 5 learns and a whole lot of environments. And then in addition to that, we'll then key map all of that, which then puts it on, multiple devices, all doing this, kind of double VMAPed learning step, which, sounds really complicated, but the like net effect of this is that you can generate just ridiculous amounts of data and have like effectively massive batch sizes. Yeah, and then to zoom out again, I explained the top part of this figure, but the bottom part is basically what we then do with the gradients, because you're doing multiple learn steps here. You could be doing like, I don't know, hundreds of learn steps, and so you've got multiple gradients here, and basically it's as simple as just meaning them and then applying the the updates to your parameters, and then doing that whole step again. So yeah, just to show you like exactly what's available in Marva. So that's kind of how Marva scales and why it's fast. But exactly what's available is we've got a variety of algorithms. So you've got your PPOs, your self-directed critics, your whole Q-learning family to QMix, and recurrent and feed-forward versions of these where applicable, and centralized and independent versions as well. Then we've also got we also support a whole lot of JAX-based environments. So all the environments currently in Jumanji. We also support some of, I think, 2 or 3 of the JAX-MARL suite, but it's super easy to support more, and we've got examples of how you would do that. And then we also support this new GigaStep environment. And so yeah, like I said, it's we want you to hack this. It's a super research-friendly code base. I'll get you now, Sanjin. It's a super, research-friendly code base. And yeah, like we have basically one file, and the core algorithmic logic is, just contained in that file. Yeah, to answer Sanjin's question, do you plan to support algorithms with communication? Totally. It's not like something that's currently on the roadmap, but in general, what we want Marva to be is a repository for algorithms that are specifically, for homogeneous and cooperative environments. There are plans to also support heterogeneous agents, but yeah, there's no reason we wouldn't in the future, support algorithms with communication. Cool. And then, yeah, the last important bit about Marva is that it's super reliable. So we've got integrated and robust evaluation with MARL eval, which Callum will talk about later. And then you've also got, general and MARL utilities such as like networks and checkpointing and logging. And the really nice thing is that if you use Marva as a starting point, and you just edit, let's say you wanted to change PPO's loss function, you just edit the loss function, you get all of this logging and networks and checkpointing and all of that for free, and the scalability, just for free, which is what we think is the really nice part of this. So yeah, I can't come and tell you that it's scalable and performs well without coming with some, receipts. So basically, the top 3 plots are comparing performance on SMAX, on the 3S 5Z versus 3S 6Z task. And it's recurrent IPPO and recurrent MAPPO. And our 2 are the graphs, and then the like flat lines are the baselines provided with the implementation of the environments. And so you can see that MARL performs equally well, or in some cases quite a bit better than those baselines. So performant algorithms. And then the bottom graph is very interesting for the speed up that you get with MARL. And that is we're comparing the performance on LBF, on original LBF with EPI-MARL to the new JAX LBF, I guess, with MARL. And as you can see, like it's basically a straight line on the straight going up, so super fast in comparison. Yeah, cool. So that's how MARL works and how it fits into the ecosystem. So as I mentioned before, uses Jumanji as like the base API. It produces like artifacts or experiment data that can be used downstream for plotting and reliable evaluation and that sort of thing. And then it can also be, I guess that stuff is then used to publish research, as well as the novel algorithms that we produce when writing MARL. And I guess that's also something important to touch on, is that we're actively invested in putting our newest research into MARL. So all of the things that we do, we use MARL. And so if we find some sort of kink that we feel isn't nice when we're doing our research, we'll update MARL and take that out or put in a new thing that we find works really well. Yeah, I see that there's another question. How easy will it be for others to contribute algorithms to the ecosystem? It's super easy. We do have like relatively high code standards, but I mean that's just a review process. If your algorithm is a good algorithm and it works, we'd be overjoyed to have more algorithms. Yeah, cool. And I'm going to hand over to Callum for flashbacks.
Cool. Hey everyone, my name's Callum. I'm a junior research engineer at InstaDeep. I have been here before, but in case you don't know who I am. Also, just to quickly speak to the previous question about how easy is it to contribute, one thing that's been interesting as someone who doesn't sit on the core MARL development team at the moment, so very involved in MARL, but not necessarily in the day-to-day, because I'm involved in some other things. I have contributed algorithms, and there's kind of this litmus test that you can use is how easy is it for me, who is not necessarily familiar with all the workings, how easy is it for me to say implement a new algorithm? And I've just recently undergone this, and it is easy. It's really, really nice. Once you kind of know where things are, and you look at that diagram and you picture where things are happening, a lot of that single file philosophy, it really benefits you, because you can easily change a loss function, or you can easily remove or add things. And once again, this is a nice litmus test, is how quickly could someone implement a novel algorithm. And I think that's quite different to some other libraries and attempts in the past, where you're kind of clicking through so many functions and you're getting to these all sorts of weird complex places, and it then becomes quite complex to implement new algorithms. So I think that's quite encouraging. Anyway, so kind of then moving on from MARL, we have Jumanji, allowing environments to live on the accelerator. We have MARL, which is this nice, easy starting place for online algorithms. But of course, we don't just want on-policy algorithms. We also want to support off-policy algorithms. And there you have a bit of a challenge where with off-policy algorithms, you have data. And so where's that data going to live? If the data doesn't live on the accelerator, we're faced with the same bottleneck as we're discussing in the Jumanji case, where if you have to exit that jittered context to grab new data from some sort of replay buffer, you will lose all the performance, you'll lose those speed gains. And so ideally what we want is, much like Jumanji, for the environments to live on the accelerator, we also want some sort of mechanism to have our replay buffer living there as well in a jittered context, allowing us to then create off-policy algorithms in Marva. And so this births flashbacks, and flashbacks is not just constrained to multi-agent RL. In fact, it's not even constrained to reinforcement learning in general. It is a buffer library for arbitrary pi trees that is just very well suited and, of course, positioned for reinforcement learning. And these replay buffers the library is very lightweight, but enables high performance in the reinforcement learning case. So I'll just kind of take you through briefly what flashbacks is. And with a code example, once again, it is pip installable. So if we think of that diagram, it's sitting on the left-hand side. It's a tool that should be pip installed, and a stable tool at that. And it's purely functional. And now this is important because it's very different to maybe a replay buffer library that we might be used to in the past, where you kind of have this natural object-oriented nature of a buffer, where you have the object, but instead, because we need things to be jittered, and we want things to be jittered, we want things to live on the accelerator, we need to make the library itself purely functional. And that means that we then need to pass around state. So we see here, we create the pure functions of the buffer, which is, say, a trajectory buffer, and then we need to initialize and have a state, and that state is then what we're going to pass to the pure functions, which feels strange at first, but I think as you use it more, and this is a theme in JAX, as you use it more, it's actually a very natural way to think about how these functions work. And so indeed, it is purely functional. And one of our pure functions is the initialization, but we also have a pure function of adding, so buffer.add there. And because it's a pure function, it's now jitterable. And so we can now compile adding to the buffer. We give it an old state, and we give it some new time steps, and then we receive a new state, which is again now this new state that we will hold on to. And we also have some nice efficient memory management techniques within this, such as in this case we have the donation of arguments, which is essentially saying donate that state memory, don't allocate new memory for it. We kind of guaranteeing the compiler, no, we'll reuse that because it's the same state, and this makes it incredibly fast. And not only is the adding jitterable, but the sampling as well, which you can imagine makes it very fast. And once again, as we saw before, we have a random number, an origin key, which has these deterministic pseudo randomness, which is very useful for our experiments. So that's flashbacks. Now you have replay buffers. Well, sometimes we also want to save those replay buffers, right? The obvious use case is for offline reinforcement learning, completely offline reinforcement learning, but there are various other use cases such as checkpointing if you have a very large scale experiment and so on. And that birthed Vault. And Vault is essentially a thin utility within flashbacks, a single file that allows us to checkpoint replay buffers for then downstream applications. And Vault is similarly very simple. So you import the utility, you create the Vault, and there you give it some sort of state experience. And so you're giving it, your structure of the data, that pi tree. And then you periodically, you give it the flashback state, and then that writes it to disk. Now, obviously, this needs to be outside of a jittered context, because now we're dealing with computer I/O, we're writing to disk. But what's useful is that that doesn't have to happen at every time step. So you can fill up your buffer with, say, 1 million transitions, which is very, very efficient, exit that jittered context, write to disk, and then re-enter the jittered context. And so there's very, very efficient memory management that you can achieve with this. And then at a later stage, now we have this on disk, we can reload that in, say in a completely different context even, we can reload that in. And that state is a native flashbacks state, if you will, which means that we can use the exact same buffer pure function, for example, to sample from it. And so there's this very, very nice tight integration between flashbacks and Vault, which is very, very useful. How does this fit into the ecosystem? As I mentioned before, flashbacks now enables Marva to have off-policy algorithms, and this is indeed what Marva uses for those. And we also have data recording to Vaults. And so then this you can kind of see how it fits into on the left as a stable and maintained software tool. And so naturally then we think, well, we have data, we can now plug into our offline MARL, offline multi-agent reinforcement learning. Now, I imagine people here are familiar with OG MARL. It's incredible work led by Claude Formanek, a member of this group. And I hope to chat briefly about it, but of course, you know how incredible the work is there. And so off the grid MARL is data sets and baselines for offline multi-agent reinforcement learning, and to kind of motivate firstly the use case of offline MARL and what it kind of is we have this data collection step, which is, say, some sort of policy interacting with the world, whether that's in a simulator or real world data. And we have all these transitions, and you know, data is ubiquitous in machine learning, and so we have lots of data. And what would be really useful is to then take that data and actually unplug. You can kind of see the little plug at the bottom of that graph. Unplug from the world, unplug from the simulator, and purely from that data set, actually learn new policies. And that's very, very useful in various industrial applications. And so that is offline MARL, and along with that, we have this need for then offline MARL data sets for us to develop our algorithms and stuff. Claude and the team saw a need for a stable, maintained repository and kind of source of data sets. And so you can see there are a variety of data sets here from SMAC and Flatland, MMU Joku across, and various others. So that kind of just justifies the offline MARL, and it's a very, very exciting field that continues to grow. So just to kind of explain some of the key features of OG MARL and how it fits into the ecosystem, we have this very, very useful experience recorder. So say you have some environment here, we have an ROware environment from Jumanji. It's very, very easy to wrap that environment, and then every time you reset and you step that environment, it's then going to add that data to a flashbacks buffer and then save it to a vault, which allows us to experience record experience when training online, which can then be used for offline training at a later stage. So here we have an example of that where we have some sort of policy. The OG MARL wrapper is sitting on top of that ROware environment here, and we're recording data, recording data as time goes on, and that data is then going to get saved into a vault, which can be used for offline MARL. Now, we also have a wide array of baselines, which are very easy to run. And you can see this command line utility, which is, say we want to download an existing vault. And so this is the stable repository of data sets. And so here's an ROware scenario. We want the Tiny4 agent scenario. Those utilities are very, very easy to use to get that data and then run baselines. And so here we have an example of running the baselines using the good data set with MAICQ, and it's very, very easy to use. And here's an example of how the vault then is used by OG MARL with these baseline algorithm implementations, and then we are able to evaluate very easily. And so, and just a mention is that historically these algorithms were implemented in TensorFlow 2, but we are in the process of moving them to JAX and really seeing the benefits of that and seeing the speed ups achieved, which is very exciting. So that's how OG MARL fits into the ecosystem, where much like Marva, it's not intended that you pip install OG MARL, but rather that you fork it, you clone it, and you then play with it, and you develop your own algorithms and you run your own things with the data sets that are provided. And then the outcome of that is novel MARL algorithms, and kind of really, really tight integration with these other things like Vault the question from Jonathan, what sort of speedups are you seeing so far in the OG MARL space? So I am not completely familiar with the numbers offhand, but I know that Claude at one point had an update in his README of changing firstly just to flashbacks, so using that as a backend for the replay buffers. And that's something that is available in the README, and I can send a link to a bit later. And then in terms of the actual algorithms, I can't say for sure, but I think the reason we're so excited is it's a perfect use case that when we can get it right, you know, if you can just have this loop that is jittered, completely compiled, and you know, you're not interacting with the real world, you're not interacting with the simulator, you can imagine the speed up that is achieved when we have the same optimizations that we've seen in Marva. So I think we're very, very excited about that direction. And so, yeah, this is the ecosystem kind of as we've presented it thus far, where we have these tools, these easy starting points, and the outcome of OGMAL here is algorithms, data sets, and then also experiment data. And so we can see at the bottom there, from both Marva and OGMAL, we have JSON experiment data. And kind of the question is, well, what is the use there? What is the importance there? And so that brings us to MARL eval. And MARL eval is for experiment data aggregation. And this comes from a NeurIPS paper in 2022 from this team. And the reason is that there was kind of a surveillance of the landscape of multi-agent reinforcement learning research, and things were all over the place. There really wasn't a nice, robust, trustworthy method for evaluating algorithms. People were doing all sorts of things. And it was very important for us to have a consistent language to talk to each other about development in the field. Otherwise, we can't actually move forward meaningfully. And so MARL eval is a tool that is also pip installable, but it allows us to really have a consistent framework for discussing our results and aggregating our experiments. And so the outcome of MARL eval is a range of plots that we can use. So we get aggregate scores, sample efficiency curves, performance profiles, probability of improvement. And these are very rigorous, robust ways to understand, say you present a new algorithm, whether or not it actually is beating existing algorithms. Can you claim state of the art? Well, these are ways to justify that. And this is definitely building on work from Agrawal et al., so the statistical precipice paper, and then indeed the paper from InstaDeep about a standardized performance evaluation protocol for cooperative MARL. To quickly take you through some of the key features, well, it kind of builds upon this standardized data structure of experiment data. So you can see here, we have this JSON file, which across various axes, we've got the environment, which then the task, the algorithm, and then say multiple runs, so multiple seeds, and then each time step within that. And that's a standardized structure, which is very, very nice. But now, not only that, we don't want to just be creating that standardized structure by hand. There's a very, very easy to use JSON logger. So here we have an example of this thing that we pip installed. We have the JSON logger, we give it the necessary details, say we use that in Marva, and we do use that in Marva, and that then produces these results for us in a very standardized way, which is useful. And now say we've got that JSON file, it's easy for us to say implement aggregate scores or probability of improvement. We can easily do that just with the same data file. And very easy to use, and you can kind of, if you've done experiments before, you can think of wrestling with matplotlib and wrestling with all these things of making sure that your data is presented in the right way. This is a nice, consistent, and robust way to do it. So that's how MARL eval sits in the ecosystem. So it's taking outputs from Marva and OGMAL, taking that JSON experiment data and producing statistically robust benchmarks and baselines, which is very important for our research. And so then to kind of cap this off, we remind everyone that the goal is for us to create impactful and reproducible research. And this whole ecosystem is striving towards that aim. It plugs into this aim of creating research that is meaningful and is reliable and useful. And so to kind of recap, we have these tools which are stable and maintained. We have these easy starting points for research, and then this community-based artifacts, right? So we want the whole community to kind of participate in this. So data sets, benchmarks and baselines, and then also ultimately impactful research. So that's the ecosystem as a whole. And just to kind of then give a flavor for what this ecosystem is unlocking for us as a team and what it could unlock for other researchers, we'll speak briefly about an example. Now, to kind of preface this discussion, the goal is not to just solve hardware. Let's see the example here. The goal is not to solve Tiny 4 agent really, really quickly in 3 seconds, right? The goal is to develop an ecosystem of tools that allows us to then take on harder problems with many more agents, much more complex tasks, say across various scenarios, not in 3 seconds, but imagine what you could do in maybe hours or days when we have this very, very efficient coupled ecosystem, right? And so this example is not the end goal, but rather a taster for what could be done. And you kind of want to think yourself, well, if this is possible in a matter of minutes, what could I do with more time? And so we have this end-to-end example of Jumanji Tiny 4 agents. And we plug that into Marva. And believe it or not, you can train feed-forward multi-agent PPO in 4 minutes to convergence. And this is on a laptop GPU. So it's not just some industry massive hardware. This is on a simple laptop GPU. And in those 4 minutes that we record the data to a Flashbacks vault, which then now lives as a static data set on disk, which we can then plug into OGMARL. And OGMARL then can recover performance, and that then plugs into MARL eval. And so you can kind of see here how this ecosystem works, how it all fits in very, very naturally together. And once again, just kind of to jog your own mind is to think, well, if this is possible in such a short space of time, the goal is not to, okay, cool, we've solved Tiny 4 agent. What happens when we scale up agents? What happens when we scale up environments and start to tackle more complex tasks to ultimately develop better algorithms for the real world? And yeah, so that's our end-to-end example, and that is our presentation. Thank you so much for having us. And if you have any questions, we're happy to field them.
Awesome. Thank you so much. I think this is, super, super exciting. I think this is, really an amazing thing to give to the community. So no, thank you for all the effort towards this. Are there any questions from anybody? So I have a question, which is inertia. It's really difficult to get people to move away from what they're already doing. What are your thoughts, other than giving talks about how amazing this is, which I think is an excellent start? What are your thoughts on actually, real world people at universities who, are doing maybe MARL research at the moment, who, there's a little bit of a barrier, even if in the end it would be much easier to use this stuff. What's your approach to actually getting people to use it?
Yeah, I think in my mind, and I believe that the team feels the same, what's really nice is we want to demonstrate the benefit of this ecosystem as a tightly coupled thing, right? It's amazing. You can see in the previous example when everything just works, and it's really, really nice. But what is also nice is that it's not a single package that you download and you have to use everything, right? Flashbacks you could use by itself, or Jumanji you could use by itself, and likewise with Marva and whatnot. So the important thing is that we've actually been seeing people say, well, I don't want to necessarily dive into Marva just yet, but I really like what you're doing with Flashbacks, so I'm going to use it. And I know that I've chatted to people at the Edinburgh lab, and they're doing that. They know that they can't, it's a big commitment to dive in, it feels like a big commitment, but they're just using Flashbacks. And I know that I think the Oxford group were using some Jumanji environments and also Flashbacks, and MARL eval is also something that we want. Okay, well, hey, even if you don't use any JAX things, even if you don't use any of that stuff, we still want people to use the MARL eval thing. Absolutely. And so the hope is that we can paint the picture that, yes, it's very important, it's very useful, that when you plug it all together, it works really well, and that's priority for us. But take what you need and kind of dip your toe in, and it's very easy to do that. And so I think, especially on the tool side, I think that's the easiest way to kind of get started is, well, hey, it would be useful to have a jittable replay buffer. And what's interesting is that OGMARL, some of the old TensorFlow systems are now using Flashbacks. So even though the training loop is written in TensorFlow, the vaults, the data sets, all of that is the JAX Flashbacks based stuff. And we are seeing massive benefits from that. And so I think that that's the answer, is that we want it to still be accessible if you don't want to kind of take on everything.
Yeah. I mean, one idea maybe would be to create little tutorial videos, like, starting from scratch. What would happen, just pip installing everything. Let's say you just want to use the Vault. What's an example of using that? That could be super helpful for researchers, I think.
Completely, yeah. And I think that's definitely on our roadmap, and in my mind is something that would be just so valuable, is to, we work with this every day, and just to kind of share with that in a very, very comfortable and low key way. It doesn't have to be a complex presentation, just to be like, hey, here is how we use it. And yeah, definitely on the roadmap.
So
oh,
sorry, go on.
Sorry. Yeah, we've specifically talked about making videos. Like, it's definitely something that we would like to do. I think it's a great idea.
Yeah, I think what you've done here with showing the code, I think is really nice. I think, if you're making videos, actually doing it like live coding is the way to go, to see, precisely step by step exactly what one would do. Would be very useful. Nice. Any other questions from anyone? So maybe I have another comment. So, because I've discussed a lot with Claude about the OGMAL side of things. I think the community aspect is super important here. Actually contributing data sets. The fact that people can run their own environments, be it using RL agents, or just playing games, like literally playing a game themselves and uploading that data sets, is a super valuable thing. And so OGMAL, the more people who use it and contribute to it, the richer it's going to be, and the more we can do with MARL, offline MARL algorithms.
Definitely. And on that point, I think something I want to reiterate is each of these libraries and tools and systems, we building in the open for the community, and we really want community participation in that. And so each of these has a person who is working on it as their job. Like, we are really taking this very seriously. And so it's the type of thing that if you feel like Flashbacks, say, doesn't have what you need it to have, ask us. Open an issue on the repo. If you're confused, open an issue on the repo. Start a discussion. We are here, and we really striving to answer questions quickly, to iterate new ideas, and very much open to that. And that's the case for Marva, OGMAL, across the board, in terms of new algorithms. And so it's really a case we call in community also to have the conversation. We want to have that conversation. We're building in the open for the community to get involved exactly in the way that you mentioned. Tim first, and then Noah.
Hey, very, very cool stuff. I just wanted to ask, in terms of like single agent support, I know that there's Stoics, a done sort of project, but like in general, is it kind of like viewed as like, MARL is kind of like a generalization of single agent. So like, single agent is just, aside from the specific algorithm, it's just kind of like n=1 for like, I guess it would also depend on the environment, but presumably you could get this to work with single agent stuff. And then also, I guess with OGMAL, I was thinking, especially with the experience, saving experience disk and stuff, that's quite similar to, the whole like imitation learning paradigm and that kind of thing, like offline imitation learning. So like presumably you could get that to work with it as well. So I just guess questions about like how general you view this as being.
As for the single agent stuff, so all the tools are completely general. So Flashbacks is, multi-agent or single agent. Same for OGMAL, not OGMAL, MARL eval, and same for Jumanji. Jumanji has a lot. In fact, Jumanji has more single agent environments. As for, could you do that to the algorithms? None of us have tested it, honestly, but I don't see a reason why it wouldn't just work if you had a single agent environment.
And I think from my perspective, obviously I can't speak to what the team's aims are going forward. Like I think at the moment we have this very, very nice the MARL ecosystem, and I'm not sure in terms of roadmap, but my feeling is that there's just such a natural synergy here to actually expand into a broader RL ecosystem. And what's really nice is we're learning a lot of lessons in building out the MARL case. And I think sometimes in building, it's useful to focus on a specific thing rather than always jumping to the most general solution. But as we build, I think we will naturally find, say with the Dunn's Stoics library, that was exactly the case where, you know, suddenly we have the set of tools in Marver, and now suddenly we have someone who's doing the single agent stuff, you know, very easily, actually. I mean, it wasn't, obviously it wasn't trivial, but he was able to build on that really, really nicely. And so I think in my mind, the vision would be that the ecosystem diagram doesn't stop there. Of course, we want to build more things in that center pillar. You know, what about more like combinatorial optimization kind of, you know, research directions, which has also been a big thing at InstaDeep. And on the left-hand side, what other tools and utils are useful, and what other libraries are useful, and what kind of other artifacts do we want? And so we want that picture to grow, and I can fully foresee, you know, maybe that means that that's a separate library on some of the stuff you're talking about, Tim, in the center. And so I think that this is an evolving thing, and definitely something that also we want the community to be a part of, you know. So at the moment, I think there's been some really nice focus that we've had in the MARL case, but definitely useful to dream a bit bigger and think of how this could expand. Yeah, thanks for the question. Yeah, Noah.
Firstly, nice presentation, guys. That was really cool. And then, yeah, my question was on a similar line, mainly just of getting people involved in, you know, the ecosystem. Presumably, most people start with single agents before they move into multi-agent. So, you know, in a way, advertising as a multi-agent system, people might get a little bit hesitant because they're committing to straight away going into multi-agent stuff. So yeah, that's, I guess, where my question also was going about, are there aims to make this more general and have it as just a RL ecosystem? And then, yeah, a very similar also suggestion with the tutorials, even if you sort of trick people in that you're giving a tutorial about a DQN or a tutorial about this, but then you use this whole ecosystem and just get people to, you know, from the get-go start using the ecosystem.
Are you suggesting clickbait?
Somewhere along the lines of that.
Classic. Yeah, no, I agree. I mean, on the first point, I think ultimately, you know, the reason Sasha mentioned it earlier is like, we are using the ecosystem and we want to build it in the open. Sorry, let me frame this correctly. We're building it in the open because we think it is very useful for the community. But more than that, we are using it for our own research. And so ultimately, there is this kind of dimension of, well, we are building the tools that are useful to us. And so right now, we are doing a lot of multi-agent research, and we find it very useful. Say with the Jumanji, there are these direct industrial applications, you know, of a lot of these environments. That being said, we definitely are open as the community grows and as the tooling grows for kind of broader horizons, I think. And then on the second point, yeah, completely. I think we're all feeling that, you know, simple tutorials would really be so nice to kind of take it through. And one example of this is currently on the OG MARL repo. There's a really simple but nice Python, just a notebook on how to interact with vaults. And those are the kinds of things we want to do more of a little bit more bite-sized. Sometimes I don't like these notebooks that are so big, and then suddenly people are just telling me what to do, but there's 100 lines of like, oh yes, let's go through DQN. But then it's like, here's DQN. And so the hope is to have these kind of bite-sized things that really allow us to understand different parts of the tools. So yeah, definitely something we want to do more of.
Awesome.
I mean, there are definitely not enough JAX tutorials as well. So if there was a
Yeah.
JAX RL tutorial, that would probably be fantastic.
Completely.
Any other questions from anybody? Oh, Tim.
I was just going to ask, did you do Gano in Marver? And if so, when are you dropping it?
So we didn't. We did it in an old version of Marver. So just to kind of be clear, Marver itself has certainly evolved over the years and has gone through various generations, which is, I think, incredible. It's incredible how a tool can evolve, and in that way, we're making sure that it's working for us, that we're making sure that it is exactly what serves us and our research. And so I think that this latest iteration is really demonstrating how useful it is for research and stuff. But when we were doing Gano last year, Marver was not in its current state. that being said, I do have dreams at night sometimes where I think, oh, it would be so nice to once again tackle Gano, and we spoke about this in the previous session when we spoke about it, that it would be nice to kind of look at Gano again, but with maybe these new tools and with these new utilities available to us.
So hopefully Sipalele is going to be looking at that.
Amazing.
So yeah,
Amazing.
he's been looking through the Gano code, and yeah, that would be ideal if he can put this into the form that can just slot directly in.
Yeah, because ideally what you want is you want a Jumanji environment, or at least something that has that same API, and then we just plug it into our existing systems, and we know that this is a very reliable starting point now, you know.
Yeah. I'm going to send this recording through to Sipalele, and he can.
Oh, wonderful.
Yeah, he can get the ideas and start on this. Yeah.
Very
awesome.
exciting.
Cool. Anything else for now? Okay, if not, I think everybody knows where Sasha and Callum and Rowan and Claude and team can be contacted. You've got all the QR codes there. But again, thank you so much for telling us about this. Super exciting. I look forward to seeing what happens in the coming months. Wonderful.
Cool. Thank you so
Thanks,
much.
everyone.
Thanks.
Cheers.
Yeah.
Bye for now.
Bye.
Bye-bye.
Yeah.